All right. Um, so we're very glad to have Calum Hughes today here from the University of Manchester talking about joint work with Adrian Miranda, the elementary theory of the two category of small categories. So you can start when you're ready, Calum.
Thank you very much. Yes, thanks for having me. It's very exciting. Yes, this is joint work with Adrian, who's also in the chat right now. Um, and we've kind of been doing this over the last year. We call it the elementary theory of the two category of small categories, and it's a kind of categorification of Lovier's elementary theory, the category of sets. So, I mean, don't worry if you don't know what these things are. We'll go through that. Okay, can I make my slides move? Okay. Yeah, so I mean, I'll start off by motivating why we would want to do this. We will review the elementary theory of the category of sets, and then I'll tell you what the elementary theory of the two category small categories is. And then, so this is meant to be an axiomatization of two categories of small categories. I'm then going to talk about some work we're doing on general two categories of categories that aren't necessarily small. Can everyone hear me okay and everything? So, yeah, okay, great.
Is it all right? It's just like,
Yeah,
yeah, I think everyone can hear you.
cool. Okay, so what the elementary theory of the category of sets is a kind of proposed categorical foundation for mathematics by Levier. This is in contrast to the traditional foundation of mathematics, which is ZFC, Zermelo-Frankel set theory with the axiom of choice. So what ZFC is, it's a first order theory in which sets are kind of built out of well-founded trees. So you start off with the empty set, and then you have some rules telling you how to make more sets, and so you get the whole list of sets. And what this does is it axiomatizes this kind of membership relation. So you've got X is an element of X, and this is the idea of this. And I mean, so this foundation is pretty good. We can do a lot of maths in it, and it's very nice. There are maybe some conceptual flaws with this. I don't want to get into too much detail into today, but suffice to say, it works for what we want it to do. Allegedly, after teaching undergraduates many classes in set theory, Levier came up with the elementary theory of the category of sets, which is a categorical reframing of ZFC, if you like. So what this does in kind of contrast is we assume the existence of a category E, which satisfies some properties, and these properties are the content of the elementary theory of the category of sets. And so what this does is it axiomatizes sets, functions between sets, and compositions of these things. So it's this sense in which it axiomatizes the category of sets. And the point is that we can do a kind of naive form of set theory here. And I'll talk a little bit more in a bit about what I mean by naive here. So the work that we're doing, or that we have done, is that we've categorified this into an elementary theory of the two category of small category. So instead of assuming the existence of a category E satisfying properties, we are assuming the existence of a two category K that satisfies some properties. And it's these properties which are the content of the elementary theory of the two category of small categories. And so these properties are first order. You can talk about them in a general two category. This is the idea. And so this should axiomatize small categories, functors between these, natural transformation, and compositions of these things. So this is the kind of idea, and so it's meant to axiomize the two category cat of these things. And the point is that we should be able to do a naive form of category theory here. So I will talk a little bit about that in a bit. But this is the kind of overview of the work that we're doing. We're taking the kind of right side of the screen and making it two-dimensional. Okay, so we're going to go and review what these properties of the elementary theory of the category of sets are now. So we say that E satisfies the elementary theory of the category of sets if it has finite limits. Pretty standard. If it's Cartesian closed, so if we've got two objects of E, we can form their exponential, and this satisfies some tensor Hom kind of thing. If it has a sub-object classifier, so this is a monomorphism from one to this object omega, such that for any other monomorphism A to B, there exists a unique map from B into this omega that causes this to be a pullback square. So in the category of sets, this omega is the two-element category, the two-element set even. So 0 and 1, this is the inclusion of 1 into 1. And so given an injection in the category of sets, we may as well think of this as a subset of B, because every injection is isomorphic to a subset of B. And so we define this bottom map here from B to omega by sending B to 1 if it came from the subset, or 0 if it didn't come from the subset. And so this defines a map from B into the two-element set and makes this a pullback. So set has a sub-object classifier. Great. And so I should say that these first three conditions give the definition of an elementary one-topos, an elementary topos. So this is an environment where you can develop a lot of propositional logic in, so you can talk about conjunction, disjunction, negation, implication. All of this sort of thing can be developed internal to any elementary topos. And these are meant to be things that look a little bit like sets, but a little bit different as well. So we need to add in a couple more axioms to pinpoint the category of sets within all categories. So we also need the existence of a natural numbers object. So this is an object n in our category, together with maps out of the terminal and a map from n to n. And this has a universal property that if we have some other thing that looks like a natural numbers object, there must exist a unique map from n into x. And so these four axioms define what is known as an arithmetic universe. And this is an elementary topos with a kind of axiom of infinity. In ZFC, that's what it is. And the point is that you can kind of develop piano arithmetic in here. But we're still not done. We need a couple more things. So we also want E to be well pointed. So this says that if we have two objects A and B and two morphisms between them, F and G, if they agree on every morphism out of the terminal, so fx equals gx for all x, then we can conclude that f equals g. So in the category of sets, this is kind of an extensionality condition. It's a kind of a strong version of the extensionality axiom in ZFC. And it says that functions are determined by their effect on elements. Okay, so we've got these five things, and then we also want, because we want a model of ZFC, we want these to satisfy the axiom of choice as well. So we can reframe the axiom of choice in set to saying that every surjection has a section. So every map from A to B that's surjective, there exists a map from B to A, such that the composite of these two things is the identity on B. And we call this in a general category E the external axiom of choice. We call it the external axiom of choice because there's a notion of internal axiom of choice, which is kind of the axiom of choice developed in the internal language of E. So that's just to make this distinction here. So yes, this is the elementary theory of the category of sets. And the point is that this picks out the category of sets amongst all other categories. These axioms axiomatize this. So, I mean, to give some examples, if we assume the axiom of choice, then the category of sets does model the elementary theory of the category of sets. That's good. It should do this. But kind of more formally, if we choose lambda to be some uncountable strong limit cardinal, then if we form the category of sets or with cardinality less than this lambda, then this is the model of the elementary theory of the category of sets. And so, I mean, formally, this is how we define the category set. We normally choose some inaccessible cardinal and define what a set is relative to this. But I want to make the point that this is actually a family of examples for any uncountable strong limit cardinal. The reason we need uncountability is so that we have a natural numbers object. The reason we want it to be a strong limit cardinal is we want Cartesian closure. So strong limit cardinals are things such that you can take the power set of something infinitely many times, iterate this infinitely many times, or as many times as you like, and it would still be less than lambda. And this corresponds to taking the exponential of 2 to the power of something and then 2 to the power of that. And we want this still to be within our set. Okay, so these are two interesting examples of the elementary theory of the category of sets. And we've also got a kind of trivial example of the elementary theory of the category of sets, which is that the one element category models what is the elementary theory of the category of sets. So this kind of is a model of it because there's kind of nothing to check. Everything holds trivially, and maybe there's a kind of way to disregard this example because it doesn't look like the category of sets, and we could maybe specify that the natural numbers object the n has to be different from the terminal object. But Levier doesn't do this, and so one is a model of the elementary theory of the category of sets. Okay, and maybe you can think of this as a kind of trivial theory in which everything is true, or something like this. Okay, to give some non-examples, as I said before, if we have a cardinal that is less than or equal to Aleph naught, then this category of sets cardinality less than this has no natural numbers object. And similarly, if lambda was not a strong limit cardinal, then we don't have Cartesian closure. The one category of small categories is not well pointed. So if we have two small categories and two functors between these things, if they agree on all maps from 1 to A, then the only thing we can conclude is that they are equal on objects. We can't conclude anything about equality on morphisms. This is because maps from one into a category by Yaneda are just objects of the category. So what is true is that if we have the same condition, if we take 2 to be the walking arrow, so just the arrow category, then if f equals df for all maps out of the arrow category, then we can conclude that f equals g. And this will feature in our two-dimensional version of the theory of the category of sets.
Can I ask a question, actually?
Of course.
About the fact that one is a model of the elementary theory. So usually one is a model of certain kinds of first-order theories, like universal algebraic theories. One's always a model.
Okay.
Say positive sort of existential theories, for instance.
Okay.
For instance, if you have the category of fields or something, one is not a field, something like that.
Sure.
I'm just wondering, can you say what sort of, so the elementary theory of the category of sets is it can be expressed as a certain sort of first order theory, I believe. Right? And I guess it's a theory presumably that only involves existential, well, I don't know exactly what it involves, presumably not unions, like that. But anyway, I was just wondering.
I think it's a geometric theory, but so like it's not any kind of in any smaller class, but yeah, it doesn't have anything that says that one isn't omega or one isn't the natural numbers object. So for that reason, you can have the trivial model as well.
Yeah. Okay. Anyway, thanks.
Great. Okay. I should say, are there any other questions at this stage, or? Okay. Fantastic. I'll move on. So yes, the category of groups is not well pointed either, because I mean, there's only it's a unique map from the trivial group into G, which picks out the identity elements, and F of this is always equal to G of this by the axioms of group homomorphisms, and we can't conclude from this that F equals G. So I mean, there's this real kind of feeling that the elementary theory of the category of sets picks out the category of sets, except for this trivial example, and it doesn't allow for kind of finite things. It doesn't allow for like two-dimensional things, and it doesn't allow for kind of algebraic things either. So maybe this is the idea. And the point is that we can develop kind of ZFC internally to a model of the elementary theory of the category of sets. So we think of our objects of this category E as our sets. We think of morphisms from 1 to X as elements of X. We think of this omega, this exponential omega to the X as the power set of X. So in the category of sets, this is the two element set to the power of X, and this corresponds exactly to the power set of X. And there's many more things you can do. As I said, you can develop propositional logic, piano arithmetic, but there's certain things you can't do. So it is true that ETCS corresponds to a fragment of ZFC, but we can't form in ETCS this set, for example, where we take the natural numbers objects, we consider all functions from natural numbers objects to the natural numbers objects, and we iterate this kind of construction and take the co-products for all of these things. And so this is a massive set. This is kind of crazily big. And what Levere says is that kind of, in everyday mathematics, you wouldn't come across something this large. So this is kind of what he means by there being a naive set theory within ETCS. But the point I'm making is that elementary theory of the category of sets is strictly weaker than ZFC. You can't form stuff like this. And so in ZFC, the way you form sets like this is by the axiom of replacement. And there's a couple of reasons why you can't incorporate replacement within the elementary theory of the category of sets. One reason is that the axiom of replacement talks about classes of things as well as sets of things. So you kind of need a notion of size to differentiate different kinds of sets. And another is that the axiom of replacement is actually an axiom schema of replacement. So it's a kind of an infinite class of axioms. So it's not elementary in this sense either. Okay, so I'm going to recall to you what the axiom of replacement is, presented in a slightly different than normal way. So if we have now this notion of classes as well as sets, and X, Y, and Z are classes, and F and G are class functions, we can say that G has small fibers if above every element of Z, the preimage G minus 1Z is actually a set rather than a class. This is the definition. And so the axiom of replacement is equivalent to the statement that if F has small fibers and G has small fibers, then their composite GF also has small fibers. And so to do a quick calculation, the fiber of GF above Z is this co-product here. So we first look at the preimage under G, and then we look at all Y's in here and look at the preimage under this and disjoint union these, and this is the preimage under GF. And so this is how we get, using the axiom of replacement, these massive co-products. So one approach to axiomatizing classes as well as sets is by Joël and Merdijk's algebraic set theory. But maybe I don't want to talk too much about that here, but this is just one way to axiomatize classes as well as sets. Okay, so that's the elementary theory of the category of sets and maybe what I want to say about it. Are there any questions at this point?
Doesn't seem so. Thank you.
Okay, fantastic. So I'll move on to talk about a categorification of this, which we call the elementary theory of two category of small categories. So, I mean, what is a small category? Maybe a silly definition to include in such a seminar, but a small category is a set of objects, a set of morphisms. Every morphism has a source target map. Every object has an identity arrow. And then we have a set of composable pairs as well and a composition operation. So this is in particular a special kind of simplicial set where the things higher than C1 are iterated pullbacks rather than anything else. And I mean, we can define functors and natural transformations, and these form a two-category cat. And our goal is to axiomatize the properties that cat has. Okay. So it turns out to be very useful to work with the definition of internal categories, which is precisely the same definition, but instead of C0 and C1 being set, these are now objects, some other category E as pullbacks. And again, we can define internal functors and internal natural transformations, and these form a two-category of internal categories. And so maybe the main conceit of our work is that because category is internal to the category of set is just this category of small categories by definition, then if we take some E modeling the elementary theory of the category of sets, then this two-category catty should look like the category of small categories. That's the main idea. And indeed, we pursue this. So the first theorem I'm going to tell you about is maybe known kind of classically before our work and maybe folklore-y, but given some references as well. So it turns out E has finite limits if and only if cat E has finite two limits. True. And also E is Cartesian closed if and only if cat E is Cartesian closed in a two-dimensional sense. And so certainly some of this was proven as early as 1969 by Bastiani and Erisman. Certainly the one-dimensional version of these theorems. So we take out two from these things. And in Adrian's master thesis, he proves two-dimensional versions of these things. So yes, this is nice. And so the proof uses the theory of limit sketches. So cat E is a limit sketch. And so a kind of theory of this tells us that we have Cartesian closure, for example, in the one-dimensional setting. Also, of use is this nerve functor that takes internal categories to simplicial objects in E. And so, I mean, to calculate the exponential of two internal categories, what you do is you think of them as simplicial objects in E. You calculate their exponential there, which exists, and then you prove that this is actually an internal category. And kind of the last bit of interest in this proof that I want to talk about is this kind of string of adjunctions here. So these will crop up again and again and again in our proofs and be kind of invaluable to us. So maybe I want to spend a minute dwelling on them. So disk is a functor from E to cat E. And what it does is it takes an object X, B, to the category, the internal category, which has objects X, morphisms X, composable morphisms X, and all of the source and target and identity morphisms between these things are just identities on X. So if E is the category of sets, this takes a set and considers it as a category in which there are no non-identity morphisms between any two objects. Okay. On the other side of the spectrum, there's this map indisk from E to cat E. And what this does is it takes an object X of E to the internal category that has objects X again, morphisms X cross X, composable morphisms X cross X cross X, and so on. The source and targets are projections here. The identity map is the diagonal map. And so again, if E is set, this gives the category which has object X and then a unique morphism between any two elements of X. Okay. And then kind of sandwiched in the middle of these junctions is this on objects. So it takes an internal category to its object of objects in E. And I mean, this string of adjunctions is so good for us because, well, for example, the on objects functor is both left and right adjoint, so preserves limits and colimits. The in disk functor is right adjoint, so preserves limits, and it also turns out to be left adjoint as well, something else, but I don't want to talk about that. So I mean, this will pop up again and again and again. These are very useful ways of transferring between E and cat E. Okay, fantastic. So I mean, yeah, this theorem doesn't introduce any new concepts or definitions. But we're going to start by giving some actually some definitions that appear new in this work, I guess, is the idea. So in a general two category, we define full monomorphisms representably. And with this, we can define a two-dimensional version of a subobject classifier. So in a two category K,
we're saying what a full monomorphism is in cat.
Yes. Okay. So it's injective on objects, injective on morphisms, and full as well. So I mean, I guess injective on objects and fully faithful is another way of saying this. Yeah.
Yeah. And so if people don't know it, do people know what representably means? You can define the concept of monomorphism in a category is defined representably. You define an arrow in a category to be mono if when you hom into it from any other object by the representable, you get an injective function. And so in a two category, you can define any sort of concept representably like that as well. So you can say that an arrow is a full monomorphism if when you hom into it, now using the hom2 functor that lands in cat, the image is full monomorphism in cat. And that's what.
Yes. Sorry, maybe I should have been a bit clearer about that. Yes. Okay.
Some master's students and stuff here. So.
Sure. Okay. Great. So yeah. Okay. I mean, yes. With this concept of full monomorphism, we can define a two-dimensional version of a subobject classifier. So we call this a full subobject classifier, and this is in particular a full monomorphism from the terminal object to omega, such that for any other full monomorphism, there exists a unique map from B to omega, making the following square pullback. So this is very reminiscent of the definition of a subobject classifier in a one category, but it's got this extra fullness condition as well. Great. So to look at an example, if we take K equals cat, then the full subobject classifier is given by this functor from 1 into the walking isomorphism. So this is the category with two objects and one isomorphism between them. And to kind of see that a little bit, if we have in cat a full monomorphism on the left, so this is injective on objects that are fully faithful, we can define a chi from B to I by taking, so on objects we do just as we did in sets. So if B came from A, then we send it to 1, and if B didn't come from A, then we send it to 0. And then on morphisms, if B to B prime is a morphism which came from A, then we send it to the identity on 1. If B to B prime is a morphism which didn't come from A at all, then we send it on to the identity on 0. And if there's a morphism from something, for example, from something that came from A to something that didn't, then we send this to the unique map from 1 to 0. And this is certainly a functor, and this makes this into a pullback square. And I should say also that the map 1 into I is certainly a full monomorphism. It's easy to check. And it's interesting to note that this walking isomorphism is the indiscrete category on two objects. So I told you that in cat, this takes a set and gives the category which has a unique morphism between any two objects. So we've got a unique morphism from 0 to 1, a unique morphism from 1 to 0, and then unique morphisms from 0 to 0 and 1 to 1. And this forms the walking isomorphism. Great. This will be this will crop up again, I guess, in this next theorem. So if we've got a category with finite limits, then E has a subobject classifier if and only if cat E has a full subobject classifier. So these things correspond exactly to one another. So to give a sketch proof, if we have a subobject classifier for E, then if we take indisk of this subobject classifier, we get a full subobject classifier for cat E, just as the case was when E was set. And conversely, if we have a full subobject classifier for cat E, then taking the on-objects functor for this, we get a subobject classifier for E. And I mean, so there was a pullback condition in the definition of subobject classifier and full subobject classifier. And because these functors are right adjoint, this preserves the correct structure. And this is kind of the idea of this proof. Okay, fantastic. We now move on to define a two-dimensional version of the natural numbers object. So if we have a two category with a terminal object, then this data here, an n, a map from 1 to n, and a map from n to n, we call this a natural numbers object in the two category K. If it is a natural numbers object for the underlying one category of K, and also if it has a two-dimensional universal property. So if we have f and g, then if n is a one-dimensional natural numbers object, we get a unique u from n to x. If we also have an f prime followed by g, by the one-dimensional property, a universal property of the natural numbers object, we get a u prime from n to x. And so the two-dimensional universal property is that if we have a two-cell between f and f prime, then we should be able to find a unique two-cell between u and u prime that makes this pasting diagram complete. So this is our definition that we're introducing. Again, if we look at the example for K equals cat, then the natural numbers object in the two-dimensional sense is given by the discrete category on this natural numbers, on the natural numbers. So to explain this a little bit, a functor from 1 to a small category A is just an object of A. Similarly, so we've got an object A and an object A prime. And then a natural transformation between A and A prime is just a morphism from A to A prime in A. So that's the data of this two-cell from 1 to A. A morphism, a functor from disk n, I've left out the disk here, but disk n to A is just a list of elements in A. So it will give something of form A, FA, F squared A, F cubed A. This is the kind of idea. And similarly, U prime will give something that looks like A prime, FA prime, F squared A prime. And so the idea is that we obtain this unique two-cell by kind of pre-composing with F. So it'll look like FF, F, FF, F squared F, F cubed F. And this defines this kind of natural transformation here. Okay, and so we obtain this theorem that if E is a category of finite limits, E has a natural numbers object if and only if cat E has a natural numbers object in a two-dimensional sense. So I mean, the sketch of this, the proof sketch of this is that given a natural numbers object for E, then if we take disk of all these things, so the discrete versions of these, this becomes a two-dimensional natural numbers object for cat E. And similarly, the other way around, if we have a two-dimensional natural numbers object for cat E, taking the objects version of this gives the natural numbers object to E. Great. Do we have any questions about this at this stage?
No questions, seems so far.
Great. Okay, so we move on to define a two-dimensional version of well-pointedness. So if we denote by this boldface 2, the walking arrow in cat, so as I said earlier, that it has two objects and one arrow between these objects. We call a two-category too well-pointed if the following conditions hold. So if we have a terminal object, if we have the co-power of this walking arrow with the terminal objects in K exists in K. So, I mean, maybe I should explain this a little bit. So a two-category is cat enriched. So it makes sense to ask for to ask if the co-power with a category exists. So here we are certainly talking about the category 2 and the terminal object in K1. Okay, and then I mean the co-power is a condition that kind of looks a little bit like tensor hom, but and a kind of an enriched version of this. And then the third condition that we need is that the family containing this co-power is a generator for the two-category K. So a generator in a two-category is well, a family of objects is a generator for the two-category K if homming out of these objects are jointly faithful. So I mean, I'll explain. It's easy to explain this if K equals cat, and maybe that will help clarify these definitions. So if K is cat, then the co-power of 2 with any objects of cat is just the Cartesian product. So then what it means for 2 crossed 1, which is just 2, to be a generator for cat is precisely this condition that if we look at all maps out of 2 into A, this is jointly faithful. So if we have two maps F and G, and these agree on all maps out of 2, then we can conclude that these are the same functor. Okay. So the theorem is that in an extensive Cartesian closed category, E is well pointed if and only if cat E is too well pointed. And the proof of this is goes by constructing an internal version of the free living arrow to E. So this is constructed in the way that you might imagine it to be constructed. So the walking arrow has 2 objects. So on object is 1 plus 1. It's got 3 morphisms, an identity on 0, an identity on 1, and a morphism from 0 to 1. So its set of objects is 1 plus 1 plus 1. Its set of composable pairs is 4 ways to compose these things. So it's 1 plus 1 plus 1 plus 1, and so on. And we just do the same thing in internal to E. So where these ones now are the terminal objects in E. And we prove this is a category, and this has the property of being the co-power of 2 by the terminal. Okay, so as another stepping stone in this proof, we show that E is extensive if and only if cat E is extensive in a two-dimensional sense. So that the property of being extensive is also inherited by cat E. And so I should say at this stage that extensivity is something that holds for an elementary topos. So we're not asking for anything strange or extra here. This follows from if we were to start this theorem by saying let E be a model of the elementary theory of the Cartesian set, then this would not be anything extra. Okay. So we move on to treat the axiom of choice.
Can I ask?
So, of course.
About the definition of generator.
Sure.
So yeah, I mean, another another alternative would be to say an objective is a generator. If you can detect two general arrows being equal, if it has the equal generator condition, but then you could also allow two cells from like the F to F prime, and
Yes.
call that like a two generator, and then sort of in cat, the terminal category would still be a two generator, because
Yes.
and so
Okay.
again, I mean maybe you could, if you used two generators, could you kick out the co-powers and then just work with sort of the discrete internal category on one as an alternative? I don't know if it's better, but it's just a thought.
Well, that's interesting. That's interesting.
So the definition that we're using is this property about detecting parallel pairs of functors, but it also detects parallel pairs of natural transformations as well. When you say two generator, did you just mean like a cat enriched generator? Is that what you meant, John?
I think so. I think so. Basically, so I mean, so an object like two there, just still calling it two, the two generator. So if you want to tell if F and G or big F and big G are the same, then you can look at just one cells from two into A and see what happens, or you can also look at two cells from two into A. So the difference being
Right.
look at one cells and two cells.
Yes.
Right.
And so it would sort of be a bit like a generator in one category theory is about something being injective, and two generators about something being injective and faithful, I think.
Yeah.
But yeah, so that is what I meant. Does that make sense?
Yeah, that is possible. Yeah, that's a good thing for us to think about. It probably is possible to get rid of this co-power by two. But I should say that co-powers also come from extensivity, so it's not actually an extra thing, even though it might seem like it is. Yeah.
Sure, but maybe it's a slicker definition. Yeah, we should think about this for sure.
Yeah. Thanks for the suggestion.
Yeah. Okay. Great. So yes, moving on to treat the axiom of choice. So we have this proposition here that if we have a category with pullbacks, the following are equivalent. So the external axiom of choice holds in E, and any fully faithful and epimorphic on object's functor internal to E has a section in cat E. So I mean, proof of this is maybe not too hard to see. That if we assume one, then epis have sections. So epi on objects functors have sections on objects, and then fully faithfulness kind of allows us to lift this to a full section. And conversely, if we assume two, given an epimorphism in E, we can consider indisk of this, and this is a fully faithful epi on object functor. So we can take a section there by two, and then take the object of this, and this gives us a section on the epi that we started with. So, I mean, the reason that I've called this a proposition and not a theorem is that this is definitely referencing the fact that K is of the form cat E. So we can't define what epi on object functor is straight away. It's not easy to define what an epi on object functor is in K, because it's for example, it's not a representable notion because epis are co-limity rather than limity. So the goal for the rest of this part is to be able to define epi on objects functors that are fully faithful in an arbitrary two category. Okay, so we do this using this lemma that there is an epi mono-orthogonal factorization system on E if and only if there is an epi on objects full monomorphism orthogonal factorization system on cat E. So an orthogonal factorization system is a pair of classes of maps such that if we have a commutative square between an epi and a mono, say, or a left map and a right map, there's a lifting between them, and any morphism can be factorized uniquely as a left map followed by a right map. So this is the lemma, and it uses this kind of more general thing that's given a orthogonal factorization system on E, we can lift it to an orthogonal factorization system on cat E, where the left class is L on objects, and the right class are R on objects and fully faithful. So this was mentioned in a paper by Burke and Garner on two categorical exactness and regularity. And I should note that mono on objects and fully faithful is exactly what a full monomorphism is, and epi on objects is exactly what epi on objects is. So we can define left orthogonal is in an arbitrary 2 category, and we can recognize full monomorphisms representably or in a general 2 category. So this allows us to recognize epi on objects functors in a 2 category. And actually, these have been studied before in a paper by Ross Street on 2-dimensional sheaf theory, in which he calls things that are left orthogonal to fully faithful monomorphisms acute, which is a cute name. But so acute maps are epi on objects maps in this setting of cat E. And this allows us to define what we call the categorified axiom of choice. And this, we say that a 2 category satisfies the categorified axiom of choice if any acute fully faithful morphism has a section. And then, so I've more or less explained the proof of this theorem, that in a category of pullbacks, products, and an epimono orthogonal factorization system, E satisfies the axiom of choice if and only if cat E satisfies this categorified version of the axiom of choice. And so I should say that having an epimono orthogonal factorization system follows from the axioms of being an elementary topos. So again, we're not adding any extra assumptions here. Okay, so this is the summary of where we're at so far. On the left-hand side, we've got the definition of the elementary theory of the category of sets. And on the right-hand side, we've got the corresponding 2 categorical properties that cat E satisfies. And a lot of these things are kind of if and only ifs. Sometimes you need to assume some earlier things in the list to make this make sense, but yes. We're not quite done though, because I said we wanted to axiomatize arbitrary 2 categories, which look like cat E. So we want to replace cat E here with an arbitrary 2 category K. And luckily, a lot of the heavy lifting of this work was done by John Burke in his PhD thesis. So there's this theorem in John's thesis that says if we have a category of pullbacks, then cat E satisfies these 5 conditions below. And conversely, if K satisfies these conditions below, then there is a 2 equivalence of K between K and some 2 category of internal categories, where this E is defined to be the discrete objects in K. So these are the objects in K such that 2 cells out of them are identities. So in cat, these are sets, and in cat E, these are these are objects V. Okay, so I don't necessarily have time to talk about these conditions, and they're quite technical. So maybe I should just say that these are these are exactness conditions to make K into an exact 2 category. But we're just going to package them up and call them Burke's axioms for now, especially as we are running out of some time. So, I mean, the point in this theorem is it allows us to recognize 2 categories that are of the form cat E for some E. And this allows us to define the elementary theory of the two-category of small categories. So we must satisfy Burke's axioms. We must have a terminal object. We must be Cartesian closed in two-dimensional sense. We must be too well pointed. We must have a two-dimensional natural numbers object. We must have a full subobject classifier, and we must satisfy the categorified axiom of choice. So, I mean, one thing to note here is that we're only asking for terminal here because one of Burke's axioms was to have pullbacks. Okay, and we write K models the elementary theory of the two-category of small categories. So to give some examples of such things, cat models this, which is perfect because it's exactly what we wanted it to do. And more precisely, we also have this result, this family of results that if lambda is an uncountable strong limit cardinal, then categories internal to this set is a model of the elementary theory of the two-category of small categories. And we also have this trivial example as well, that the one object two category is a model of the elementary theory of the two-category of small categories just by trivial things. And so the main theorem in our paper is that E models the elementary theory of the category of set, if and only if cat E models the elementary theory of the two-category of small categories. And in this case, E is equivalent to the discrete objects in cat E. Moreover, if we have a two-category that models the elementary theory of the two-category of small categories, this happens if and only if discrete objects in this model the elementary theory of the category of set. In this case, K is of the form cat of disk K. And the kind of third thing is that this actually extends to a biequivalence. So we can form very large two categories of models of these things. So the objects of this left-hand side thing are models of the elementary theory of the category of sets. Morphisms are functors which preserve the structure, and two cells are just two cells. And similarly on the right-hand side, this is actually a biequivalence. And so, I mean, this extends some results in Burke's thesis as well. This is using another theorem from John. Okay, so it is in this sense that we have categorified ETCS. So we, to the same extent that a category E models the elementary theory of the category of set, a two-category K models the elementary theory, the two-category of small categories. And this is meant to look like the category of small categories. So do we have any questions at this stage or guess?
It doesn't seem so.
Okay, I think I only have a couple of minutes left.
It's not that big.
I think
if you need a few minutes. Like...
Okay. Sure. Okay. In which case, yeah, I will try not to rush too much, I guess. Great. So, okay, so the point is at this point that models of the elementary theory of the two-category of small categories give a setting which you can do small category theory in, but real category theorists don't really care about small categories as much as they care about arbitrary categories, maybe. So we want to extend this to not being just about small categories. Moreover, the elementary theory of the two-category of small categories is kind of equivalent to the elementary theory of the category of set, and the elementary theory of the category of set is, corresponds to this fragment of the ZFC, and maybe we would like to incorporate replacements into this theory to give a model of the whole of ZFC, or something that's equivalent to the whole of ZFC. Okay, so as I said earlier, the first three conditions of the elementary theory of the category of set gives the definition of an elementary topos. The first three conditions for the elementary theory of the two category of small categories do not give the definition of an elementary two topos in the sense of Mark Webber. And that's because this kind of full subobject classifier is not the right kind of classifier, or it is not the kind of classifier that's considered in Weber's work. So instead, he considers the notion of a discrete lock vibration classifier. So let's talk a bit about that. So in cats or category of small categories, or we can think of some larger category of categories here. A discrete Hopf vibration is a functor from A to B, such that if we have an A and A and a morphism from B to F of A, then we can lift this to an A prime in A and a morphism from A prime to A that maps down onto this thing. So this is the definition of a discrete Hopf vibration in cats. And in a general 2 category, we can define these representably. So yeah, homming out of these, it gives a discrete Hopf vibration in cat. I also want to recall the Grothendieck construction. So the Grothendieck construction takes normally a pre-sheaf, but we're going to ignore ops here. So takes a functor from A to set and constructs a category of elements of F, so which we're denoting LA of F. And one way to see how this works is to take the functor, the forgetful functor, which takes pointed sets, so sets with a choice of elements, and forgets that choice of element. And then the Grothendieck construction is just a pullback of this functor F along P. And so this defines a functor from two functor from cat A from functors from A to set into discrete Hopf vibrations over A. So the point is that this left map from LAF to A is a discrete Hopf vibration. And we have to work in certainly large categories here because the category set is not a small category. But kind of the point is that this map this discrete Hopf vibration is small, so it has small fibers. This LA of F is actually a small category. So that's interesting. And this functor LA is fully faithful as well. And it is these properties that Weber kind of generalizes into and gives the definition of a 2 topos with. So a discrete Hopf vibration classifier for K consists of a discrete Hopf vibration such that for any X and K, the functor which takes the pullback of the discrete Hopf vibration classifier along F is fully faithful. And given such a thing, a discrete Hopf vibration classifier, we can define a notion of small discrete Hopf vibrations if it features as in the image of this functor. And we can also define what is a small object relative to this discrete Hopf vibration classifier. And so yes, the definition that he gives of elementary 2 topos is a category with finite 2 limits, Cartesian closure, a duality involution, and a discrete Hopf vibration classifier. So I don't necessarily want to say anything about this duality involution today, but it's something that is desirable. And the point is that the category of small categories is not a 2 topos, rather the 2 category of larger categories is. So now there's this notion of size that is kind of differentiating our example. So if we return to the axiom of replacement, we also had this kind of notion of size thing that was that made us unable to incorporate it into the elementary theory of the category of set. So we had classes X, Y, and Z. And the point is that this version of the axiom of replacement is equivalent in cat to the statement that small discrete vibrations are closed under composition. So if we have a small discrete vibration from A to B and a small discrete vibration from B to C, then the axiom of replacement implies that GF is also a small discrete vibration. And conversely, if we have this holding, then if we look at classes and take the discrete functor to make it into functors between categories, then this forms small discrete vibrations exactly. So this is equivalent to the axiom of replacement. And Schulman's idea is that in a general two category, if we have a discrete vibration classifier, then the condition that small discrete vibrations closed under composition is a two categorical axiom of replacement. Okay, great. And this gives us our definition of two categories of categories. So if we have a two category with a discrete vibration classifier, I said that we could define what a small object was. And if we take the full sub two category of small objects, we have this inclusion here. And we say that this K, along with this discrete vibration classifier, is a two category of categories if the following conditions hold. So if both of these two categories model the elementary theory of the two category of small categories, if this inclusion is a morphism of models of ET2CSC, so it preserves the structure, and if small discrete vibrations are closed under composition. So this is the axiom of replacement. Great. Just to wrap up, this setting is an example of such a thing. So large categories with this discrete vibration classifier. And it turns out the category of small objects is the category of small categories. And so we need some maybe set theoretic conditions to make this precise. We need an inaccessible cardinal mu and a bigger strong limit cardinal. And if we define size relative to these two things, then this all works out formally. Great. So work that we're currently doing with this is that we've shown that two categories of categories satisfy Schulman's two-dimensional algebraic set theory, or at least we've shown most of this. We've still got one condition to show. This is work in progress. We also want to be able to define free co-completions in a two category of categories. I've got some ideas of how to do this under co-products, for example. And we kind of conjecture that this might give a more genuinely two-dimensional version of a natural numbers object, which axiomatizes the category of finite sets rather than just being the discrete version of the natural numbers. And we also want to prove that we have co-equalizers in the elements theory of the two categories of small categories. So, I mean, the point of all this work is to find a setting where you can develop synthetically two category theory or normal category theory inside it. And so we would really like stuff like co-equalizers and free co-completions, stuff like this. So yes, I should finish there. Half of this has been worked out and written up into a paper that you can find on the archive. The other half hopefully should appear soon. But yes, thank you very much. I welcome any questions.
Thanks very much for a great talk. It's really interesting. Does anyone have any questions? Comments? Yeah, go ahead.
I have one. So in this full sub-object classifier, so there was the condition that was there was only one dimensional. So it was nothing. There was nothing about. So is it?
Sure.
Does it automatically satisfy some sort of two-dimensional universal property, or? It seemed.
Let's go back. That's a good question. I don't know. I don't. Maybe
so
Adrian
in the paper we do kind of that there is a remark about this. There's like a choice that you can make here. One seems kind of like a better two-dimensional choice that to make in terms of what the two-dimensional universal property should be, but then you just get something co-discrete indiscrete rather than what you want. I'm also struggling to remember exactly what it is, but it is in the paper. If you wanted to look at that section, there is a remark where we do talk about what the two-dimensional version should be, and we do give genuinely kind of a two-dimensional definition in the paper as well. So yeah, sorry I didn't have it right off the top of my head right now, but yeah, but it is there.
It's yeah, it's very late in Australia right now.
pullback there is like two pullback, I guess, as well. Is it?
Yes, I guess
It is,
yes.
yes.
So yes, I mean, I've maybe left off some of the details on this slide because it wouldn't fit otherwise. But yeah, it does have a kind of two-dimensional property as well. But I mean, maybe part of the kind of gap between a full suborbs classifier and a discrete off vibration classifier is part of this. We want genuinely two-dimensional things happening, or something like this.
Any more comments or questions? I would just say, yeah, I mean, it was nice to see that you used this theorem in my thesis. That was
Yes.
my favorite result of my thesis, but nobody ever seemed very interested in it. So
Oh,
I
great.
didn't publish it or anything, but so I was really pleased to see that someone used it for something.
No, I mean it's
Yeah.
I mean in some sense this is the heavy lifting of our entire work. So I mean it's really important and useful.
Thanks. And yeah, no, but um I never looked at the smallness sort of related stuff that's coming up in your future work.
Sure.
Sounds quite exciting as well, and related to, so it seems like you'll be working out. I mean, there's a lot of open questions about two-dimensional elementary topos theory, and this sort of
Sure.
all seems very connected to this, so it seems quite exciting.
Yes. So I mean I should maybe mention that a two category of categories is a elementary two topos in the sense of Weber, because we've got this a classifying discrete op vibration, and this duality involution comes from just taking op in this cat. So so yeah, it is an elementary two topos.
Okay. And is the duality involution condition, what do you think of that condition as part of the definition of
Sure.
topos? Or
I'm honestly I'm not sure I understand its place in there, but it's something that Schulman and Weber both say should be in there. I don't know if
So,
Adrian.
yeah, I'll just say something very briefly. I mean, obviously, two categories of the form cat E have this duality involution by just sending a category to its opposite category. However, if you want to have, two categories of, two-dimensional pre-sheaves on a two-category, which are definitely Grothendieck two toposes, and you can look at sheaves as well, but just pre-sheaves even for now. If you want them to actually be elementary toposes, then it doesn't seem like they have a nice duality involution. I think a PhD student of Nicola's, Luca Massetti, was talking to me about this earlier. So it might be that certain things we want to call elementary two toposes have these nice duality involutions and others don't. So yeah, it's that one is less obviously needed.
very good. So yeah, so well, it seems like lots of you are working out the details of these things in Manchester, so it seems quite. I look forward to hearing. Look forward to hearing
Yes,
about.
sure.
Any more questions? Well, if not, then let's thank the speaker again.
Thank you.
And yeah, so I'll stop recording.